Earth is mostly water. If a large asteroid slips past our tracking systems, probability dictates it will likely end up in the vast Pacific Ocean. Many assume that because the ocean is fluid and largely empty, a water impact would result in a harmless splash far from any populated coastline. But physics changes at hypersonic velocities. When rock meets water at thousands of miles per hour, the liquid doesn't have time to flow or displace gracefully. The ocean density acts like a high-speed transmitter, converting the asteroid's kinetic energy into a series of mechanical waves that threaten the entire planet. The moment the rock breaches the surface, it obliterates the water in its path, instantly throwing millions of tons of ocean into the sky. This is a transient crater. The sheer force pushes the water column aside, exposing the dry seabed below. As that void forms, intense shockwaves radiate horizontally from the crater walls, pulsing through the water at thousands of miles per hour. When the surrounding ocean eventually rushes back to fill the void, the opposing walls of water collide at the center, firing a secondary pillar of seawater straight into the upper atmosphere. Ground zero may stabilize in minutes, but the kinetic energy injected into the system creates a chain reaction that will last for years. The first threat moves away from the impact site as an invisible wave of energy traveling through the open sea. In deep water, this energy travels as a submerged mechanical pulse, racing at nearly 600 miles per hour, the cruising speed of a commercial jet. This diagram illustrates shoaling. As the pulse hits the shallow continental shelf, the wave compresses and its vertical height grows exponentially, transforming into a mega tsunami. Coastal emergency systems would trigger immediately, but the extreme velocity of the wave leaves very little time for local populations to reach high ground. Because this horizontal ripple travels so fast, it eliminates the traditional warning windows that communities rely on to survive oceanic disasters. While the waves move outward, a second disaster moves upward. The initial impact blasts a column of steam and debris straight into the stratosphere. This injection contains millions of tons of vaporized salt, water, and pulverized rock, suspended miles above the Earth's surface. As the debris spreads, it triggers the albedo effect. The particulate layer acts like a mirror, reflecting sunlight back into space. This solar reduction causes rapid drops in global temperatures, disrupting weather patterns necessary for agriculture. The vertical ripple effectively converts a localized ocean event into a multi-year global climate crisis. Monitoring a disaster of this scale requires a shift from local observation to a macro view of our global infrastructure. Meteorological and oceanic data must be routed across international borders in real time to model the path of both the clouds and the waves. Orbital satellite networks, shown here in this topology map, provide the only way to track the vapor plumes and tsunami vectors simultaneously across every ocean basin. This data allows for the mobilization of international relief operations, prioritizing the coastal zones projected to face the highest risk. Because the physical effects of an impact expand radially across the planet, the survival of these regions depends on high-speed international cooperation. Current data suggests that we are better prepared for these events than at any other point in history. Global space agencies maintain a continuous surveillance grid, specifically designed to track near-Earth objects well before they reach our atmosphere. By calculating orbital trajectories years in advance, scientists can confirm that the paths of known large asteroids currently remain at a safe distance from Earth. These what-if models allow researchers to stress-test emergency protocols and identify the most effective ways to defend our coastal infrastructure. Quantifying the mechanics of an ocean impact confirms that our long-range tracking systems are the primary tool available to ensure these physics are never put to the test.